now it's working. So,
Oh, okay.
success. Just took, apparently, the threat of me using a different type of technology. It's like, oh, I can't be replaced. Let's see, where am I at? All right, so we were talking about molar solubility, and we just started talking about the common ion. So the common ion, like we talked about on Wednesday, reduces the solubility of a salt when you are in the presence of a common ion. And like we did on the problem on Wednesday, we make the approximation that the amount of common ion added will be large compared to the amount of ion coming from the insoluble salt. So let's do an example problem that puts that into practice. Let's see, do I have it on the next slide? Nope. Let's say, for example, calculate the molar solubility of, what's a good salt? We'll do calcium difluoride. First, just in water, and secondly, we'll have a solution that contains 0.250 molar calcium nitrate. So the first thing we're going to want to do is determine what the molar solubility is in just water. So what are my two products that get made from calcium difluoride, or calcium fluoride, not difluoride, calcium fluoride being produced? Okay, calcium plus 2, and then how many fluorides? All right, so we do our little ice chart. Why do I draw an arrow through that? Why don't I have to calculate the concentrations of that? It's a solid, right, so it doesn't affect our overall concentrations. And we imagine we start off with none of that. So at equilibrium, we are there. All right, so then what piece of information do you need to go to the back of the book and look up? KSP. And KSP for this calcium fluoride is 1.46 times 10 to the negative 10th. So now what's my first step to get X all by itself? All right, divide by 4. Then take the cube root. It's a 4. It's a smidgy looking 4. Smidgy. It's like a smudge. Not exactly. It's a smidge of a smudge. So smidgy. Mm-hmm. All right. Which ion is that the concentration of? Calcium. Okay. What if I wanted to figure out the concentration of the fluoride ions. Okay. All right, so that's just the calcium fluoride in water, predicting the two ion concentrations. All right, so then part B was I now have a solution of this calcium solution. So what do we expect to happen to the concentration of the calcium ions? Will there be more calcium ions or will there be less calcium ions coming from the calcium fluoride? There should be less coming from the calcium fluoride. What would we expect about the concentration of the fluoride ions? More will appear or less will appear? It should be less, right? Because if there's less calciums, then there should also be less fluorides. So let's double check. All right, so now I have a concentration of 0.250 of the calciums in solution. And I still have 0 initially at the fluoride. So I'm doing the second step and the third step of the ice table. Ran out of space, so I'm going right over here on the side. All right, what's the approximation we can make at this point? Right, this small x is going to be very small compared to our 0.25, which we know it's going to be in the ballpark of 3.3 times 10 to the negative fourth, which is 2 order of magnitude smaller than this. So we know for sure, within reason, that this x is small, which makes our calculations easier. So now I have 1.46 times 10 to the negative 10th equals 0.25 times 4x squared. So then take a second, do the algebra to get x by itself. I guess something in that ballpark. 1.2 times 10 to the negative fifth. All right, what is that the concentration of? It would be the calcium, which we can double check. I mean, our approximation was that it was small, so before it was 0.250. So add that 0.250. Still true. All right. Because it'd be 0.250001. That's a good approximation. What's the fluoride ion concentration? Yep. So did the fluoride ion concentration decrease as we predicted? From here to here. Yeah, right, the fluoride ion concentration decreased, which is what we expected. The free calciums coming from the salt also decreased. It went from to the -4th down to the -5th. So our predictions, our math matched our predictions. So that is good. Very, very good. All right, questions on how to set up any of those kinds of problems? All right. Let's talk about a letter we haven't talked about in a while. Q. So the question is, how do we know when a precipitate will form? The answer is by comparing our KSP and Q. So at what point of the reaction is big K true? All the time, just one spot in time, starts with an E, at equilibrium, right? KSP is by definition, in its name, is at equilibrium. Where Q is everywhere but equilibrium. Right, before we compared, is Q less than K, is Q greater than K, is Q equal to K? Right? What could we say about the reaction if Q is equal to K? We're at equilibrium, right? And if we are on one side of K or the other, we could say Le Chatelier's wise, which way we should go to get to equilibrium. We are going to do that as a review, but now talk about ions in it. I know, it's pretty awesome. So let's say, here's my example. All right, so I have silver iodide, which makes a silver ion and an iodide ion, right? If I wanted to write the Q expression for this reaction, what would be in the numerator? Okay. What would be in the denominator? 1, right? Because it's a solid. So you're going to write it like your KSP expression, just we're going to talk about Q. And then these were the 3 spots we could possibly be, right? We could say okay, so where am I at if Q equals KSP? I'm at equilibrium. Can I put any more ions into solution? Or am I at the max number of ions? You're at the max number of ions, so what do you call that kind of solution that's maxed out on ions? Saturated. Okay, so if Q equals KSP, we know both we're at equilibrium and the solution is saturated. Okay, let's take a look at the other 2 sides of this. Let's do if the value we calculate for Q is less than what is known to be KSP. Is the solution saturated? right? If I get a concentration of ions that is less than it could possibly be, we are not saturated. Right, if we find that KSP is 1 times 10 to the negative 10th, and our value of Q is 1 times 10 to the negative 4th, no, the other way, negative 12th. Right, we're on the negative side, so we have to have a number smaller. I could add more ions to get the KSP, right? You could, so we're not saturated. So which direction is the reaction going to go? If we are not saturated, am I going to go towards products, or am I going to come back towards reactants? We're going to go towards products, right? We want to make more ions. So if there is still some of the solid, if there's still solid silver iodide in there, it'll keep dissolving till we get to equilibrium. Let's say you're out of silver iodide as a solid. What could you shake into your beaker to get to equilibrium? What could you forcibly add to it? More of the ions, right? You could add a common ion. So you could add silver chloride, or you could add sodium iodide. Right, so you can forcibly add some more to get to equilibrium. How do I feel about that? Good? Makes sense with what we know about Le Chatelier's principle? All right. You guys are mute today. I don't know what. A whole week of class just exhausted you? Is that what it was, having to actually come to class every day? The whole week? All right, so let me do choice 3. So what's the third choice? Oh, yeah, Cody. Oh, All right, so I have Q equal to KSP, Q less than KSP, Q greater than KSP. All right. So I picked a random KSP. What did I pick over here? 1 times 10 to the negative 10th. And now I'm at a Q that is 1 times 10 to the negative 4th. Let's say that's where I'm at. Am I exactly at equilibrium? So am I saturated? Okay, I have a greater Q than KSP, so am I undersaturated? I am not under, I am oversaturated. When you put a common ion in there, you can get to the point of oversaturation. And that's the actual technical term. It's supersaturated. It's like they were coming up with words and they're like, it's like supersaturated. We'll go with that. Supersaturated. So you can either be undersaturated, saturated, or supersaturated. So what is going to happen to our reaction, if this is our reaction, what's going to happen to our reaction to get back to regular saturated? Are we going to move towards products or move back towards reactants? You got to move back towards reactants. So this is the point where you'll actually start to form solid. You'll see precipitation fall out of your solution, precipitates, fall out of solution, until we get back to the point of equilibrium. So let's do a practice problem that puts that into practice. Let's say, for example, you're in the lab and you have a solution that has a lead 2 concentration, .00120 molar. Probably should have done scientific notation. It's a lot of zeros. So you have a solution that has a lead 2 concentration of 0.00120 molar. You're going to add enough chlorides until the chloride concentration is 0.01 molar. Question is, where are you in the reaction? Will you form a precipitate? So, what is the thing you'd look up in the back of the book about this that you need? KSP, okay.
This is the KSP of lead.
Excellent question. What's going to be made? If I have lead 2, I told you, it's going to be that. This right here. Never mind, it's not your question anymore. I actually gave you the answer. No, it's not. All right. All right, so now I have 2 things initially in my solution, right? I have both those concentrations in there. So then we do this step. So what assumption can I make about this reaction to help out with the crazy math we're about to have? Both the x is small and the 2x is small compared to these larger molarities.
So it still does apply to the 2x?
It does apply to the 2x. But you still have to square the second one. Let's see, what does that turn out to be? What is that negative? 1, 2, 3. Oh, yep. So I'm going to keep, oh, question, Bobby. All right, so now we need to look at, here's the Q we just found. Here's the KSP. Are they equal? No, so I'm not at equilibrium. Is Q greater than or less than KSP? Is less than. Will you have any lead chloride precipitating? No. Because we are undersaturated. So you would have to add more chlorides than what we added to get to the point that either we are at equilibrium and or supersaturated. So we're not there yet. So the answer is no, you'd have to add more. Okay, I got one more problem for today. This will maybe pull it all together. Because I think I'm out of PowerPoints, right? That's the last PowerPoint. Yes, okay, good. All right, here's my last question for today then. And then we'll do some other stuff on... I forgot to include in the PowerPoints. I have one or two more things I want to cover in this chapter about complex ions that we'll do on Monday. So my last question about common ions will be this. Let's say so I have silver nitrate being added slowly to a solution that has 0.02 molar chloride ions and 0.02 bromide ions. I want us to calculate the concentration of silver ions. I want us to precipitate silver bromide and not precipitate silver chloride. So first thing we're going to do is we're going to look at what are the balanced chemical equations for both. Then we'll look at the KSPs, and then we'll start making some predictions. All right, so let's take a look at what two ions does silver bromide turn into? Yeah. Just checking, making sure everybody's still conscious. So the KSP for that reaction is 7.7 times 10 to the negative 13th. Our other reaction has a KSP of 1.6 times 10 to the negative 10th. So which solid, silver bromide or silver chloride, has the smaller KSP? Right, silver bromide has a smaller KSP, so it should precipitate first. Right, if you're thinking about it, you require less ions to precipitate. It's a smaller KSP, so it should precipitate first. Which is good, right? Because I want to be able to precipitate the silver bromide and not the silver chloride. Either bromide would go first, they'd both go together. And then you'd have to like reverse it. You can do it, just be a lot more work. So, first thing we want to find is find the silver concentration required to precipitate silver bromide, given we know the concentration of bromide. You don't even need an ice chart for this, right? Because the KSP right, we know KSP, we were given the bromide. You could put into an ice chart, you'd end up with X is small. And so you just end up with the same concentration you had before. So when you get confident, you can skip the ice chart. All right, so let's see what that is. That's not right. All right, so what does that tell me about how much silver I need to add? Is this the high end or the low end? That should be at equilibrium. So that's the bare minimum silver I need to add to get this to work. How can I figure out the maximum amount of silver I need to add?
Find the concentration of silver to precipitate the cyanide.
Right. We want to find the concentration of this silver ion using this KSP, because when we get to that concentration of silver ions, we now start precipitating the silver chlorides, which is what we don't want. So this is the low end. Issue. So 8.0 times 10 to the negative ninth would be our high end. So to precipitate the silver bromide and not the silver chloride, you need to add enough silver chloride, or silver ions, to get to at least this molarity, but not so much you're at this molarity, because then you start precipitating the wrong thing.
So you just use the lower KSP, calculate the lower.
Yep.
And the higher, the higher.
Yes. Pretty straightforward. How do I feel about that? Confident. Pretty good. All right. Here is my plan for Monday. Based on your quizzes, we were just very speedy today. Based on your quizzes, you guys have no idea what's going on in titration. No idea whatsoever. I'm pretty much totally baffled. So my plan for Monday is to do the titrations again. Go through titrations, when to use a regular ice chart, when to use the IACE ice chart, how to make a prediction about pH, how to draw a pH titration curve, things like that. So we're going to do that again on Monday. We're just going to do titrations. So I don't have any PowerPoints for it. We're just going to do a bunch of titration problems and work through them. I do have your quizzes to give back, so someone from your group, make sure you come down and get them. You guys were just